after oh god, sorry, coffee. After giving it another thought, I don't know. I don't think this is gonna lead me anywhere. The creation of a design of a different gate that would kind of not have the side effects of the Hadamard, because I realized that thinking about this, I kind of realized that the effects of the Hadamard are not as much fault of the Hadamard, but also it's a combination of the Hadamard's action and the fact that we are acting qubit at the qubit level, right? So, um, and at the end of the day, the the fact that we play Hadamard here is implicitly acting at the level of, these two squares, right? So if we wanna detect another pattern, then it's not that you need another gate. You might, but it's not just that, because if the fact that you're applying it to this qubit will always kind of restrict you to the pattern between these and these, right? So if you want to detect another pattern between other areas of your amplitude list or matrix, you would need to implicitly first do some kind of rearrangement, which is at the end of the day what the swap does, right? So because at some point I was thinking, why don't we just do sort of a first operation? Because it seems to be the first step is the only one that needs to be corrected, then everything goes well, in terms of the hardware applications. But then I was like, well, yeah, kind of. But that's kind of the same as doing the swap, right? So you just do the swap in the very beginning and then change the controls and all this kind of stuff, so they match the proper wires. That could be one way to easily explain the inverse QFT, as in you say basically the swaps are to prepare the data in a way that then the Hadamard can pick up the right patterns. But it still feels a bit artificial in terms of trying to explain what the algorithm is doing, because then you probably have to start with the Hadamard on the top, which is like, why? Because I like the interpretation of we're starting here because we're basically trying to identify cycles, right? So I want to stick to this interpretation. The fact that we're trying to identify cycles. Remember that if can I basically stick to the example of 4. I'll get rid of all these. If I've got that basically, right? And if so I need another harmonic here. I need a control, and I basically need a. So this is going to be 1 minus 1 divided by 8, and then we've got a copy of this and a copy of this that go here and here. I mean, at the end of the day, what's kind of really happening here, right, is that you're trying to identify the cycles, right? So pay attention. Here we've got 1, right? So obviously, if you've got a 1 here, right? The other way around. So when you apply Hadamard here, right? You're gonna fold that. You're gonna first of all gonna tell you what's the relationship between this part and this part. In the simplest cases where we're talking about pure frequencies, right, and not like mixed set of ones, you're basically gonna have 2 options or two possible outcomes. One is, well, they are the opposite in terms of phases, right? You can see this is 0, this is 180, this is the opposite of this, etc. In which case, it means that we are in the middle of a bigger, like, full round, right? So we kind of gone through the half, because it means that the next half is going to be the mirrored half. So this tells you in this case that, you know, it could be 1, right? Another way to look at it is if it's equal, right? If here we've got like a 0, regardless of what else that we got here, doesn't matter. Like, the pattern is always the same, because basically what this is telling you is that so if this repeats the same, it can only mean that the number that we're going to have in here is even, right? And the way that the Hadamard picks that up is by saying they are the same. So I'm going to fold that superposition into the 0 half, into the half where that qubit is 0. So this stays empty. And so, and I think this is exactly where my whole idea now kind of like exploded, because I just realized that, so wait a second, so basically at that point, we already know, of course, what's the qubit going to look like in those cases, right? I think for a superposition, for a more complex wave, is going to be a bit more complicated to understand or to explain, but I think we can do a good job there as well. So, and so basically, I just didn't realize until now that, well, it's actually trivial to see that, because in this circuit, there's nothing else happening to this wire. I mean, it's used as a control, but this kind of control usage in here can be it's rather, I think, can be seen rather as the, you know, if the qubit is 1 or 0 type of thing. And I'm trying to exactly. So this is basically telling you already that that qubit must be 0, because yeah, because it's going to be an even, regardless of it's going to be an even number, right? An even frequency, and that's why there is a swap at the end. It's just really confusing. It's just, I think the problem here comes to the fact that you're used to read a circuit like, you know, kind of step by step, right? Like this step, this step, this step, this step, this step, blah blah blah. And then when you get here, it's like, why are we swapping? But it is actually easy to understand if you think about the same way that you think about QFT. The same way you think about QFT here, as you're not understanding these swaps. Like, the first time I said that, it's like, well, you gotta understand this, not just as, you know, this is an operation, and so just we do it because. Like, I realized that you need to understand that in conjunction with the rest of the circuit. Why are we swapping? We're swapping because that's what we want to build, is this kind of cyclic pattern of data. And so you want the values that have a 1 to basically go here, and cascade, and then kind of activate some of those controlled operations, because they're going to control a series of rotations that is going to, you know, then in conjunction with the Hadamards, which are creating the superposition for you. So this is going to create the right type of rotation, because each qubit has, based on their power of 2, value within the number that's represented, because it's a binary number. They're going to have a certain impact on the rotation of the phase. So these rotations are only, and that's why the rotations are powers of 2, right? 8, 16, 32, 64. So it's, so you're just kind of using the binary representation of the number as a way to rotate. So, and then that's why this also makes sense. Now, you can think about the inverse of the QFT, or the QFT. I don't know if I think I kind of stopped. That is QFT. No, that is the. I like to think a bit about this a bit more like the inverse of the QFT, and this like the QFT, because it's more like QFT is like going from phase encoder wave to an actual frequency, and that's what the Fourier transform does. And I know, Craig, that it doesn't really matter that you can, that QFT 3 times is the same like the inverse QFT, because those things are cyclic, but it just makes more sense to me. Um, so you can think of this in the same way. It's just that where you're coming from the phase encoder wave. So you're basically trying to detect patterns, detect cycles. You're trying to detect the cycles, right? So you're saying, good. So if we have like a cycle here that falls into the zero part, it means this has to be even. So that's why we do the swap, right? And so then you've got now this part, and now you say, okay, so the first thing that we have to do is, did this fall into one, right? Because if it falls into, that's I think still. Let me try to explain this. I'm not so sure I fully grasp the rotations or the interpretation of the rotations here, but if that's supposed to fold into one, right, it's because, let me see. So it's because this was an odd number, right? And so when we've got an odd number, when we've got an odd number, we should correct these, but the type of correction here, I mean, and this is short, like this notation, basically, this can and probably should be better represented like this, just for the sake of understanding really what is happening here, right? Like I don't know if this is a thing for, it's like a convention that you can pack them all in one column, but Craig does this a lot, and you can do this in Quirk. So now that rotation, basically, what is supposed to do is supposed to correct, what is supposed to correct? The fact that we now want to take a look at the contributions of what? So basically now we've got the one is fixed, right? So now we got so now we're going to take a look at the comparison between this row, which is all zeros on the second qubit starting from the left, and all ones in here. All ones in here. These, though, have to be corrected because in the original, let me see, in the original input data, this is the comparison of these here and these here as a pack together with these here and these here. So the difference here is you can see that they are kind of like 90 degrees apart, right? Because those are like 0 and 180, and this is like 90 and like 90 and minus 90. So if you consider like these and this is like one pack, and this is the other one, so you're comparing the green and the violet or lilas or whatever the color that is. This is they're 90 degrees apart, and so the Hadamard is not going to work really well there. You want to correct that so they are kind of like either 180 degrees apart or 0 degrees apart. exactly. So, but because we're picking one of each, I mean, we're picking one thing like that here, so we gotta, uh, is that, so I see, I don't fully, I see the need for that, but I'm not yet entirely sure why this works, but I'll promise you that I'll do an executive summary where this is really fully understood. The thing is, if you, if if let's imagine that this is the number, so this is the qubit that's activated. That this qubit is activated. What's the difference between? So now they're like 90 degrees apart, and if this is activated, they're still 90 degrees apart, but they are opposite. Uh-huh. The point is, you see, and take that for granted, yeah, take that for granted for now, but you see that that the pattern that you're going to pick up here reflects the influence of that qubit, not that, of that qubit, right? And so here, whether this is going to be like, whether we're going to basically stay with the rows where this is 1 or with 0, that basically is telling us what's the value that that qubit should have, what's the influence that qubit should have. So, and I don't know if you, but when I don't know if you see that, but when I started going through this, I was like, wait a second, there is a way to build the QFT without the swaps. So look at this, basically, you can basically do that if you don't care about the amount of qubits, right? So let me see. After each Hadamard, we know what the contribution should be for a particular qubit. So basically, after the Hadamard, right? So let's get rid of the swaps. Sorry, no, let's keep the swaps in here just to compare. Let's have here at the end this, and let's have here at the end this. So basically, as I said, if this guy here, this qubit is 1, then we know that this qubit must be odd, right? The whole number must be odd, which means that this qubit must be 1. And if it's 0, this qubit the whole number must be even, so this stays 0. So, and a similar reasoning goes for the next controls. So here, if this guy is 1, then this should be 1. If this is 1, this should be 1. And if this is 1, this should be 1. And voila, right? So basically, you don't need that anymore. So you've got like you've basically got a QFT without the swaps. It's just that you need twice as much qubits, and your outcome register is the one in the bottom, the output register. So this is the output register, this is the input register, right? Of course, this is useless because, as you can see, the only thing that kind of keeps you keeps you away from compressing it into the 4 qubits is just adding the swaps at the end. But these kind of breaking it down this way help me understand really what are the swaps they're doing. They are actually assigning the right weight to the right qubit. So the Hadamard is picking up the Hadamard is the thing is the Hadamard is picking up cycles, but these cycles, the outcome of applying the Hadamard is telling us what is the impact of the first qubit, because you know, if this is going to be fault into a zero, then we know that's going to be an even number. The reason, like, it's because of, I mean, that's what we're doing here, right? So we're saying if this is a, like we're saying, if this is a one, if here we've got a one, please go down here and activate the biggest chain of rotations, because why? Well, because it's not going to be an even cycle, so it's basically not going to repeat itself at that point, right? Yeah. Whereas, whereas if it's a zero like now, right? Once you're at that point in creating your superposition, right? Here you've got half of your stuff full. So now you're saying, okay, so now you're gonna say, is this gonna be is this an even number? If it's an even number, then we just want to double the same cycle, right? So that's why if it's a one, right? We're basically sorry. Yeah, what I was doing. So if it's a zero, we just want to double the existing data that we've got here. So that's why then we just need the Hadamard that's waiting here, and we don't need those rotations. So bam, right? And then you've basically got it doubled. It's difficult to move those things around. Whereas if it's if it's an even like an odd number, right? You want this one to basically activate a series of rotations that then what they do is that they take you down here in the half where this is one, and so when you will apply the Hadamard, how can I do that? Yeah, that's gonna be better. Exactly. So now you're basically, with these rotations, you're getting ready to then apply the last Hadamard that is gonna double and mirror that, right? So you're doubling and mirroring, so you've got the desired structure, which is the fact that this is just half of the cycle that so that's what the role of the swaps is here, is to basically compute the final wave, phase encoded wave, based on the right influence that each of the qubits will have, and so you can read this in the same way, basically. So this is it's simpler than I thought. I thought it would be fancier. I don't know. I thought I would have to design, as I said, like a whatever gate, but then I realized that it's not the keys. It's not the fault of the Hadamards only. It's a combination of these. It's just the fact that if you want to detect cycles, right? You're basically, these cycles are influenced by you can detect cycles. I'm struggling to find the right wording. The influence of the first cycle you can detect in here is influenced by the qubit that is sort of the rightmost in our representation, right? Or that will be sort of the lowest contribution qubit. Because if it's odd, it means that the whole thing is just split in half, and they're two halves of one bigger picture. And if it's even, it means that that basically that you're that it's that the half kind of repeats itself, right? Um, so I hope this is clear enough. I really hope that's clear enough, but that's basically it. I mean, now does this work for fancier inputs, right? I was thinking a lot about this, and I was afraid that we would get some kind of um, nasty nasty decoherence or whatever. And we do, but in terms of the phases, right? That we can't really detect the final phases, but the amplitudes will be correct. So, and as far as I've read people talking about this, and people say that it's a free built-in feature of quantum computing, that if it works for single amplitudes, and it should work for superpositions as well, because it's sort of it's a consequence of the linearity of the operations. Um, but I'm not 100% sure that's always the case. I mean, I'm assuming if you mess up with the circuit and build something that is not the way it's supposed to work, then that might not really be true. But I'm willing, I mean, I'm basically willing to test this here, and I think it works because if I create let's say that we want to have, how do we going to do this? So let's say we want to have, here we've got, as an example, we've got just one single amplitude, right? 0, 0, 0, 1. Let's try to have two, right? If I apply Hadamard here, now I basically have 1 and 3. So now it's a mixture of 1 and 3, right? Yeah, and I already see that it's working, 1 and 3. You see? So you got, it says incoherent because you can't, I think the reason it says that is that you can't really calculate the phases and even the amplitudes because it's entangled with the qubits. I mean, because it's a subsystem, right? Okay. If measured. Yeah. But we see that's the outcome we get. I mean, I'm assuming that's correct. And I guess the reasoning behind this is, yeah, and that would be your phase encoded, your phase encoded data. That's interesting though. That's a fancy thing. So this has 0 amplitude. But basically, the idea here is it was easier to understand this when we just had one, right? Because you could see the patterns unfold. But here, it's like, what's going to happen with the Hadamard? Well, let's go through the different steps. Here, we do pick up a pattern cleanly, right? I think where we are not going to pick up a pattern cleanly is, so after this Hadamard, yeah, after this Hadamard, we see, yeah, you see what happens when I move the Hadamard from the front to the back. So basically, this Hadamard doesn't pick a clean pattern because after applying these corrections, I mean, and you know, it's just not. And this is, in hindsight, I realize it's because I put the Hadamard in here, right? So basically, what this is telling you is that this is not like a clean pattern, right? So when you're now going to do that qubit here at that point, if you take a look at the Bloch sphere, it's not, but you see it's not 0 or 1, it's not even it's really, 50-50% chances of each. So I think, and it's a bit entangled. So the thing here is basically, that's not, this is the contribution that we want to associate with that qubit down here. But this is still going to work because basically what the control knot will do in this case is kind of keep track of both possibilities, and that's why we ended up creating a superposition for the outcome here, whereas like, in some cases this qubit might be 0, and in some cases it might be 1, and that's the actual qubit that is this one here, right? So you see the difference, the third qubit from the left or the second from the right, it's 0 here or 1 here. So that's what we want exactly. That's why it also works for more complicated superpositions. It just, because of the linearity of these operations, like that's going to keep track, like even if this qubit is not like a clean 0 or a clean 1, if it's like somewhere in between, it's still going to it's going to translate that into our outcome registry. So that's awesome. That's really cool. Yeah, that's pretty cool, man. That's really nice. So it works as well for that, and yeah, that's nice. So here we see that if this is the one, if this is the qubit, like that, this is what we have the difference, then we already see that we don't pick up the right pattern after the first Hadamard, like a clean pattern. Oh no, wait a second, we do pick a clean pattern here, do we? And I think, yeah, it's a clean pattern everywhere. Well, where we don't pick up a clean pattern is here, I think. Yeah, exactly. Cool. That's even fancier when you've got like something like these then, right? Now I've got 4. So basically you've got, yeah, but it works. It works. So you can see these and these are the same. Perfect. And yeah, this basically tells you, it's cool because this really tells you why this whole thing works in the first place for no, so it tells you why the swap gates are needed there. You're doing the same thing, just using the same 4 cables, 4 wires, right? You're just saying, okay, now I picked my Hadamard, like my Hadamard picks a pattern, and so at the end of everything, I know that this pattern that I picked in here is the one that should belong to that qubit, simply because that's kind of how you would generate the cycles. The lowest value qubit is affecting you, is kind of influencing the latest, like the big picture cycle, whether it's going to be repeating itself or whether it's just a half of a bigger cycle, and that maps to whether it's an even or an odd number, which basically can be just determined by that qubit in here. So I know that I probably repeated myself 3 or 4 times, but I just wanted to kind of make sure that I understand this myself. So I think that's definitely it. So here you have the QFT without swap gates. Yep.